Okay, so at this point now, we're able to finally calculate the last method for estimating effective population size, and that's by looking at the variance in reproduction. This can be done because we have tediously tracked each random parent and how many offspring they have produced. So at this point, we can calculate the number of offspring for individuals 0, 1, 2, 3 that are males. And so we'll be tracking how many offspring did each of these individuals actually have. We'll use another homegrown array function to do this. Our first question is going to be, is the dad equal to individual 0? So we'll need to reference the dad cell, column F, and we'll simply ask, is this equal to the value stored in cell O23? And remember, that's going to return true or false, an array. And we're going to multiply that by another question. And this question is going to be, is the offspring number actually part of the offspring population? So is the count equal to 1? And we'll anchor the references to both the dads and the offspring. And what this is doing again is it's doing this multiplication pairwise. True, false, true, false, true, false. So the dad has to be a 0 and the count has to be a 1 in order for that element to become a 1. And we'll wrap the whole thing into a sum function, and that will tally all of the offspring for dad number 0. And we'll enter that with Control, Shift, and Enter. And you can see here that individual 0 was pretty prolific and produced 21 offspring. So here he is, random dad 0. There he is again, 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 again. And the reason is because there's quite a few offspring in this next generation, and there's only 4 or 5 dads to begin with. So that's not too surprising. We can copy this number through, and we will get the output for each and every one of our males. So individual 4 sired 12 offspring, individual 0 sired 17. Now how about the females? We can copy this over and simply make some adjustments. Here we're interested in the random mom. We press Control, Shift, and Enter and copy that through, and we then end up with the random mom. And let's just double check that work. And I can see by this double checking that I have made a mistake. I need to drag my individual reference back over to column O and then press Control, Shift, and Enter. So then by this calculation, individual 0 for the female sired 13 offspring, or had 13 offspring. So let's find her. There she is, once, twice, 3 times, 4 times, 5 times, 6 times, 7, 8, and so on. So we are down, this was to 56 individuals. We have to go to 100. So these numbers are looking pretty accurate. So our next step is to calculate the average reproduction for males and the average for females, and then we'll sum or total those. We'll look at it from both perspectives, and these variables are called K and V, and we'll use those in our effective population size calculation up above. So let's start with the average for the males. Well, here we can use a function called the average if function. Here it is, average if. It's very much like the sum if function. We're first going to specify a range, and here we are only going to consider the individuals that are in the parental population itself. So we're only considering those individuals that have the criteria of the number 1. And if that's the case, then we are going to then average them. So here we'll select all of our numbers of offspring and then press OK. And it looks like I made a mistake in my entry here. Instead of a plus, we need a comma. So the average for the males is 20 offspring. Still not surprising. We had 5 males, and in the next generation we had 100 individuals, and so our males had each contributed on average 20 individuals to the next generation. How about the females? We can copy that over and make some adjustments. For the females, we want to reference column D. And we end up with the number 10. The total is going to be a little bit trickier because we need to consider the average across both the males and the females. And we can't just average those two numbers. So what we're going to do is we're going to take the males average and multiply it by the male population size that's stored in cell C14. And then we'll add the females average, multiply that by the female population size, and then we'll divide the whole thing by the total population, which is going to be the sum of the males and the females. So our average reproduction for the whole male and female population considered together is 13.33. And you'll see that's different than simply just averaging those two. Now how about the variance? Well, there is a variance function in Excel called var_p. And the var_p function calculates the variance, but again we're going to need to restrict it because we only want to consider the parents that are actually in the population. Here's var_p. This counts the variance for an entire population. So we're not sampling in this spreadsheet. We're considering these populations, and this is the population we're interested in. We know what everybody's doing. Now here for the number 1, we want to ask a question, and here we're going to specify a condition. And that condition is going to be if the males are equal to 1. So we'll go ahead and choose column B, and we'll ask if they are equal to 1. And if they are equal to 1, we're going to take the variance of the numbers of the males here. So we're calculating the variance of the males. And this has to be entered as an array function as well. And I think you're probably trying to get the idea that this is a very powerful way to enter equations into Excel because it lets you have all kinds of freedom to do different sorts of calculations. We need to enter this as an array function, so we'll press Control Shift and Enter, and that should generate the variance in the population for the males. And let's just double check that. I'm going to enter var_p, and I know that I have only 5 males, so we'll check the variance for the first 5 males. And you can see that it's returning the same answer here. We want to enter it as an array though because we want the spreadsheet model to be very flexible so that whatever we throw at it, the calculations will work in the long run. Let's copy this over for females and make our adjustments. So for females, we want the female to be equal to 1, and we want to calculate the female population. And we'll press Control Shift and Enter, and that generates the variance of the females. There are 10 females. Let's just double check that. The variance for the females is going to be equal to the first 10 individuals and that matches cell P18. Okay? So there we have the variance of the males, the variance of the females, but what we need is the variance of the total population, and this is our last calculation. And here we'll use the var_p function once more, and you might have noticed that you can enter this in different boxes here. I'm going to use the first box to calculate the males and then the second box to calculate the females, and that should actually compute things correctly. So the first box is going to include an if function. If the males are equal to 1, we want to take the variance of the male output. So that's our first set of numbers. And our second set of numbers will be the females, and they are stored down column D. If the females equals 1, we are going to take the variance of the reproductive output of the females. Close the parenthesis, and then once again we are going to need to enter this as an array function. So if I press OK, I'll get an error, but if I head back up into the formula bar and now press Control Shift and Enter, then it will return the number. And again, take some time, double check this math. Make sure I haven't made a mistake. But these are the numbers we're going to be using for our final effective population size calculation. Phew, a lot of work. But we think you'll have some fun with this model later when we play with some questions in the sandbox. So the first thing we're going to do is to take the average and the variance that are stored in Q17 and 18. We'll copy those and we'll paste them into cell R5 and S5. And we'll paste the values and we'll transpose them. So choose Paste Special and then choose Values, Transpose, and then OK. And these represent K and V. So now we can just enter the equation as we have it. The effective population size is K times N times K minus 1, N times K minus 1, divided by, and now here for the denominator, I'll go ahead and put it in parentheses, V plus K times K minus 1. Close the parentheses twice, and that will give us our estimate of the effective population size when we consider variance in reproduction. But like I said, at this point now, we're going to be able to really explore how changing and fluctuating population sizes will affect NE, how changes in the sex ratio can affect NE, and also how changes in the variance in reproduction can affect NE. So at this point, we will pass you on back over to Jed, and we'll see you a little bit later when we start to explore and really give this spreadsheet a workout when we do some exercises in the sandbox.
Great. Thank you very much, Terry. I hope you found that exercise to be helpful in terms of understanding this notion of effective population size and also how you may calculate it in various ways. So we've covered a fair amount in this module, and just to wrap up, let me hit a couple of the key points. For one, effective population size is a means of characterizing a population from a genetic perspective. And so from a technical point of view, we would define effective population size as the size of the population of an ideal population that will lose genetic material at the rate of our population in question. So it's the size of an ideal population relative to our larger population. And that ideal population will lose some genetic material through processes like drift. and inbreeding. So if we have a population, let's say, of 1,000 individuals and an effective population size of 100, that means that the large population is equivalent to or behaving genetically like a much smaller population, one that would be ideal at size 100. And when I say ideal, I mean one that has random mating, has an even sex ratio, it doesn't change in population size over time, and it has a relatively even amount of reproductive output among individuals. Individuals are contributing equally their amount of genetic material to the next generation. So effective population size is very useful in terms of characterizing the genetic makeup of a population. Now, we've calculated it in various ways. You can estimate it for a population that is changing. It's very useful in circumstances in which you believe that a population may have gone through a bottleneck, as we've covered before. It's also very useful for estimating populations that have a very skewed sex ratio. I've covered African wild dogs, for example, but there are others that experience very higher, I would say higher levels of sex ratio imbalance than wild dogs. We've also seen that effective population size can be influenced by uneven reproductive output among individuals within a population, and we ran through a calculation that allows you to estimate it in a circumstance like that. So what we do know about effective population size is that it tends to be a lot smaller than the real population size in question. So a real population of 1,000 that has an effective population of 10, for example, creates some conservation issues. So we may say, all right, our population of 1,000 is in good shape. There are a lot of individuals there. But in reality, it's behaving, it's equivalent to a very, very small population. And that small population, right, that effective population size, means that it's losing genetic material, heterozygosity, diversity, much faster than we might expect as if it was 1,000. So that can create some challenges from a conservation perspective, and it's certainly good information to have. If we're interested in maintaining a certain level of genetic diversity in a population, for example, knowledge of effective population size might steer decisions we might make about reintroductions. It might guide the way we plan or find stock for reintroductions. It may give us an indication for the level of inbreeding that might occur in that population, and may give us a means of managing for this issue of genetic drift and loss of genetic diversity. So with that said, you should have a good understanding of what effective population is, why it's important from a conservation point of view, how you can calculate it in a variety of ways for different populations with different characteristics, and more importantly, how it might relate to some of your own work.